What if we already found it? A planet that could actually support life, sitting there right now. And here's the thing, we might need to get there sooner than we think, because contrary to popular opinion, Earth isn't actually the best planet for us. It's already wiped out nearly all life on it across 5 separate mass extinction events. And it's not just other species. At least 20 other species of humans have already gone extinct here too. You don't need science to feel that. Just spend a day outside without shelter, food, or medicine. That's exactly why TRAPPIST-1e is such a big deal. It circles a small, dim red dwarf called TRAPPIST-1, a star that's actually gentler than our own sun and can keep burning steadily for trillions of years, while our sun has only a few billion left before it swells up and destroys everything close to it. So, how long would a real mission actually take? Surprisingly, there are real funded projects already working on getting us there faster than you'd expect. Let's find out. TRAPPIST-1 isn't named after some massive space agency or some billion-dollar flagship mission. It's named after a telescope in Chile, about the size of a large truck, run by a small team of astronomers with a fraction of the budget bigger observatories get. In 2017, that modest setup found 7 planets, roughly Earth-sized, several sitting in exactly the right zone for water to exist. One of the smallest, quietest instruments we've ever pointed at the sky found the best candidate for a second Earth humanity has ever come across. Now this word, budget. Sit with it for a second. Let me share a fact. In 2024 alone, the world spent roughly $2.7 trillion on militaries. Now I want you to compare that to NASA's entire budget for that same year, for every mission, every telescope, every planet it studies. About 25 billion. The world spends more than 100 times more fighting itself in a single year than it spends trying to understand what's actually out there. And still, with a fraction of that, using a modest telescope most people have never heard of, we found this. And it's not the only search underway. Humanity has now confirmed more than 6,000 exoplanets, out in every direction, using every method we've got. So the real question isn't whether we're looking, it's why, out of 6,000 worlds, this particular one is the one everybody keeps coming back to. Most of those 6,000 worlds were never real contenders, massive gas giants, scorching orbits closer to their star than Mercury is to ours. Planets so far away, hundreds or thousands of light years out, that even the best telescopes we have can barely tell us anything real about them. TRAPPIST-1 is different, and it's different in a way that almost never happens. It's not one planet in the right zone, it's several, all circling the same small dim star, all roughly Earth-sized, several sitting close enough to that just right distance where water could plausibly stay liquid. Astronomers don't usually get that many real chances in one place. Most systems give you one shot if you're lucky. TRAPPIST-1 gives you several all at once, all worth checking, and it's close, relatively speaking. 40 light years isn't nothing, but compared to most of those 6,000 candidates, it's practically next door. That's why, out of everything we've found so far, this is the one system that keeps pulling scientists back. Nobody's confirmed it can actually support life. Not yet. But suppose for a moment that everything about it turned out exactly right. What would actually be waiting there? Even in the best case, it wouldn't look anything like Earth because of one detail that changes everything. TRAPPIST-1e is tidally locked to its own star, the same way our moon always shows Earth one face. One side sits in permanent daylight, the other permanent night. And because it doesn't tilt or wobble the way Earth does, there's no escaping that either. No seasons, no change, ever. Whatever day it is when you arrive is, in every way that matters, the day you'd live in forever. Picture actually standing there. On the daylight side, directly beneath the star, it's the hottest point on the whole planet, baked constantly by light that never moves. Walk far enough toward the edge of that hemisphere, and the star sinks low, huge and red in the sky, hanging roughly 3 times larger than our own sun looks from Earth, frozen in place like one endless, unmoving evening. And look up, and it wouldn't just be the star. The other 6 planets in this system orbit so close together that some of them would hang in the sky large enough to actually show detail. Clouds, maybe even surface features the way our own moon does, not just distant points of light the way planets look from Earth. Keep walking, and you'd cross into permanent night, cold, dark, lit only by stars, with the wind never fully stopping, because heat's still trying to move from the side that has it to the side that doesn't. Here's the honest part though. For a long time, scientists assumed a planet like this had to be a dead end. One side cooked, one side frozen solid. More recent modeling actually pushes back on that. Even a fairly modest atmosphere real climate simulations suggest could carry enough heat from the day side to keep the night side from ever fully freezing over. Some researchers even argue tidal locking might not be the disadvantage it sounds like. It could make the planet's climate more stable than Earth's, not less. But that's only true if the atmosphere is still there at all. And TRAPPIST-1e isn't the only planet in this system we've already checked. Its 2 closest neighbors, TRAPPIST-1b and 1c, already have an answer, and it isn't a good one. Bare rock, both of them, their atmospheres stripped away entirely by their own star. And here's why. TRAPPIST-1 is a red dwarf, and on a calm day, red dwarfs are actually gentler than our own sun. Stand under one, and you'd absorb a fraction of the ultraviolet radiation you would here. They also live far longer, burning steadily for trillions of years, long after stars like our sun eventually run their course. But red dwarfs have a temper. When they flare hard, hard enough to have already stripped the 2 planets closest to it completely bare. So the real question isn't whether TRAPPIST-1e could theoretically support life. It's whether its atmosphere actually survived this long, or whether the star already stripped it away the same way it did to its 2 neighbors, and whether we'll even be able to tell from here. So how do we actually go find out? TRAPPIST-1 sits about 40 light years from Earth, roughly 9.5 trillion kilometers for every one of those light years. The fastest object humanity has ever sent into space. Voyager 1, moving since 1977 at about 61,000 kilometers an hour, would take roughly 700,000 years to cover that distance. Modern humans have only existed for around 300,000 years. Our best real spacecraft would take more than twice that long just to arrive. Here's the problem with that. If Earth ever became unlivable and we needed somewhere else fast, 700,000 years wouldn't help us at all. That's not a backup plan. That's longer than we've even existed as a species, twice over. So if Voyager's the best we've got, is there anything faster actually on the table? There is something faster, and it's not science fiction. It's called Breakthrough Starshot, a real funded project using gram-scale probes riding a light sail, pushed by a massive ground-based laser array up to roughly 20% of the speed of light. At that speed, TRAPPIST-1 wouldn't take 700,000 years. It would take about 200 years. That's a genuine leap forward. But here's the catch. Starshot isn't built to carry people or supplies or anything except a tiny probe designed to fly past and send data home. Nobody boarding that trip ever arrives anywhere. So what if we actually wanted to send people? There's a real answer to that too. A design called Chrysalis, a genuine, currently proposed spacecraft, 58 kilometers long, built to carry entire generations toward our nearest star, Alpha Centauri, over about 400 years. Nobody who boards it would ever see the destination. Their descendants would. Apply that same design to TRAPPIST-1 instead, roughly 9 times farther away, and that trip stretches out to nearly 4,000 years. Something like 16 generations, born, raised, and gone, entirely aboard a ship before anyone actually arrives. Even Starshot's probe has a problem of its own though. A single gram-scale spacecraft is too small to send a signal back that could ever actually reach us across that distance. So researchers have proposed launching not one probe, but an entire swarm, potentially 1,000 or more, working together to relay a signal back home in stages. There's one more idea worth mentioning. Some physicists have proposed ships that scoop their own fuel as they fly, pulling in hydrogen scattered through space and burning it in an onboard reactor, so the ship never needs to carry fuel at all. It's called a Bussard ramjet. The catch: interstellar hydrogen is so thin that the scoop would need to stretch thousands of kilometers wide just to gather enough, and the drag from collecting it might cancel out most of the thrust it produces in the first place. So even with our best real ideas on the table, faster helps. It still doesn't come close to solving this the way we'd need it to. There's one more idea though, and it's stranger than all of these combined, because it doesn't try to shrink the distance at all. So why not just push past even Starshot's speed? Every bit of extra speed costs fuel, and fuel has weight, and past a certain point, the numbers just stop making sense. Even reaching something like half the speed of light, fast enough to genuinely change every number in this video, is completely out of reach with anything we've built or seriously designed. And there's a hard physical ceiling past that anyway. Nothing with mass can ever actually reach light speed itself, no matter how good our engineering gets. But there's one idea that doesn't even try to beat that ceiling. It works around it entirely, not by moving faster than light, but by changing how time itself behaves for whoever's making the trip. So back to the question we started with. If TRAPPIST-1e really is everything we're hoping for, how long would it actually take us to go find out for ourselves? Using our fastest real spacecraft today, roughly 700,000 years. Even a real working generation ship would take nearly 4,000 years, 16 generations, born and gone before anyone arrives. But there's a third possibility, and it's stranger than either of those because it doesn't shrink the distance. It shrinks time itself for whoever's making the trip. Back in 1963, the astronomer Carl Sagan worked out what would happen to a spacecraft that could accelerate constantly at exactly 1 g, the same pull of gravity you're feeling right now, sitting still on Earth. Push at that steady rate for about a year, and you'd already be approaching the speed of light. Keep going, and something genuinely strange starts happening to time itself. Picture it. You're on that ship. A year into the trip, gravity feels completely normal, same as home. But outside, everything is already moving differently than it should. Reach TRAPPIST-1, and by some real calculations, a journey like this could take you somewhere around a decade or so of your own life. Meanwhile, back on Earth, 70, maybe 80 years would have quietly passed. Everyone you left behind would be gone before you ever arrived. You wouldn't have traveled through space alone. You'd have traveled forward through time just by moving fast enough. Sagan's own conclusion was even wilder. At a steady 1 g, he calculated that the entire galaxy becomes reachable within a single human lifetime for whoever's on board. Not because the ship somehow beats the speed of light, because for the crew, time itself slows down enough that the trip simply doesn't feel as long as it actually is. Here's the honest catch though, and it's not really about physics anymore. It's about engineering. Nobody has ever built anything that can sustain that kind of acceleration for years at a time. Some of the same scientists who studied the Bussard ramjet, the fuel scooping idea we already talked about, have specifically looked at whether it could be the engine behind something like this. Their answer in 2022 was the same problem we already ran into. The scoop would need to be enormous, and the drag it creates might undo the very advantage it's supposed to give you. So the honest answer is that we don't yet have the engine, but we already have the equation, worked out over 60 years ago, sitting there, waiting for the engineering to catch up to it. A couple hundred years back, people thought the open ocean marked the edge of the world. It didn't. It's worth remembering that before deciding anything here is permanent. So no, we can't reach TRAPPIST-1e in time to matter right now. But the thing standing in our way might not be distance at all. It might just be that we haven't yet built something fast enough to slow time down for whoever's willing to go.